Hey there. So this is our second kind of sequence of videos here that has to do with solutions chemistry. So the first few videos that we had were more about like what is a solution, what's happening at the molecular level, what's concentration, what happens if I add more water, those sorts of things. This second series here now is going to go more into depth into types of chemical reactions and sort of seeing some of these types of chemical reactions, and then using that knowledge to be able to predict outcomes of chemical reactions. That's not all in this video. This is just the start. But a lot of times students will ask this kind of question all the time, like, hey, when do we blow things up? Students a lot of times are really surprised when they find out that a lot of times in chemistry, that when you combine two things together, absolutely nothing interesting happens. It's like, wait a minute, I thought things were going to start on fire, right? This is the common meme. So part of this video is to help you kind of learn to recognize some types of chemical reactions so that as we get a little bit more sophisticated, you'll be able to start to make some predictions as to, yeah, that's going to happen, or yeah, no, that's not going to happen. So that's really all this is about. So there's two major ways that we can take a look at balanced chemical equations and organize them in a way to help us predict products or predict outcomes of it. So technique number one, which is I'm going to show you in these next couple screens here, is sort of a structural method. In other words, looking at the general form of the equation and being able to say, oh, that looks like a synthesis, or that's a single displacement or double displacement reaction, by looking at the reaction type. And those are really useful because it helps us to predict what kind of products we might be able to make. And if we know what kind of products we have, then eventually we can start to predict whether or not the reaction will actually occur, which is a different question. And then I'll go to a different technique later on, technique number two, that's more functional. It's taking a looking at the forces that drive chemical reactions forward. So this first part here, you were probably introduced to this back in Chem 1 when you're starting to balance equations. One of the skills that we try to teach students is to start to look at them and sort of try to make sense out of them. So they're not just, alphabet soup, right? Letters and numbers and arrows and pluses and things everywhere, but to start to see some patterns. So here's two of our simplest types of chemical reactions that occur. And that was what we would call synthesis reactions here and decomposition reactions. These are two of our simple ones that work out pretty well. I'm going to switch my pen here to give me something a little bit more functional. A synthesis reaction is exactly what it sounds like. You're synthesizing. You're taking two relatively simple reactants and combining them together to make a more complicated product, a more complicated compound of some sort. So the simplest version would be element plus element makes compound. That's the very simplest type of synthesis reaction. You can see an example of this over here on the left, where we've got sodium plus chlorine gas. If we put those together under the right conditions, they can indeed synthesize table salt, sodium chloride. So just because we say A plus B doesn't mean that there's no coefficients or no subscripts or anything like that. You still have to balance charges and do all that kind of stuff. But it's that element plus element to make compound. This is a more complicated version, a little higher level version of a synthesis, where we actually have a simple compound and another simple compound coming together to make a more complicated compound, right? You're rearranging the bonds and making a new product that's just slightly more interesting than the two things that it began with. So I don't want you to think too strictly about this idea that it's A plus B. Sometimes it could be AB plus CD makes ABCD, right? It's making basically one larger product. That's a synthesis reaction. And decomposition is basically the mirror image of that, where you're taking a relatively complicated reactant like AB here, and you're breaking it down into its simpler components. You're literally taking bonds away as opposed to putting bonds in. And so typically we would write this in its simplest form as compound breaks down into element plus element. And that's kind of what this first example is right here, where we've got nickel 3 oxide is breaking apart into nickel and oxygen gas. It's a pretty straightforward decomposition reaction. But again, just like what we did in synthesis reactions, sometimes it is slightly more complicated. So here we've got a carbonate, zinc carbonate, and it's breaking down into a zinc oxide and a carbon dioxide. So we've got one larger compound and then two simpler compounds as products. Those are both decomposition reactions. So again, it's kind of building something up or breaking something down. It gives you an idea, synthesis and decomposition. Our next phase here is slightly more complicated, right? Getting a little bit more interesting in terms of their structure. And these are called single displacement or double displacement. You'll also hear them being called single replacement is another thing that this one is called as well. Double replacement, not as much, but single replacement is a fairly common name for this one. And what single displacement is it's literally that. Displacement means one element is kicking out or displacing another element. So here we have a compound, A and B are together, and then C comes along, and C is going to displace one of those two from the compound. And so you can kind of see now here we've got the new compound form where B has been displaced. Now, is it B or A that gets kicked out? Well, it depends on what this is. If C is a nonmetal, then it will kick out the other nonmetal. If C is a metal, then it will displace the other metal, right? It just depends. It's going to take the place of the similar type of element that it is. So again, there's an example of single displacement. C comes in, bullies these guys, and then kicks B out. And again, that tells you something about what C and B were, that these had to both have been nonmetals. So here's a case where these are both metals, and you can see an actual case of a single displacement reaction. If I take a chunk of zinc and I drop it into a solution of copper 2 chloride, the zinc is going to kick out the copper and take its spot. It's going to displace the copper. So now zinc has paired up with chlorine to make the compound zinc chloride, and copper has now been displaced as a single element. Single displacement or single replacement. Double displacement is a little more complicated looking, and in fact, it can look quite complicated. But usually with double displacement reactions, the hallmark of this is that you've got a compound and another compound, and they're switching partners. It's almost like a foil, right? Like an first outside, inside, last, right? But it's just first and outside or something, or it's outside, inside. So typically what you'll get is a new combination of ions, and this is sometimes called ion exchange, where this is a positive ion and this is a negative ion. And this is a positive ion, and this is a negative ion. And so you're swapping partners so that you get the new combination of A and D going together. There they are. So it's kind of that outside, and then you'll get the inside will combine together, the other positive negative compound. You would never have A and C together because they're both positive. They're going to repel one another. Same thing with B and D. They would be two anions and they would not bond together. So double displacement is just switching of partners. So what gets complicated though sometimes is that our ions aren't necessarily single elements. For example, down here, our ions are polyatomic. So this would be our A and nitrate would be our B. C would be copper and D would be chloride. But in this case, the nitrate ion is acting as a single piece, right? It's a single polyatomic ion acting as a single functional unit. And so what we get as our two new products is copper and nitrate together. Here it is. And silver and chloride together. And here it is. Again, still just swapping partners, but double displacement reactions can look a lot more complicated. We're talking about these plenty over the next couple of videos. And then our last one, if you're just talking about a simple, relatively simple structural reaction type, is the type of reactions that we call combustion reactions, right? Fire. Not all flames are combustion reactions, but pretty much all combustion reactions produce some fire. Not all of them, but most of them do. And with combustion reactions, these are actually very simple structurally. You always have oxygen gas as a reactant. You always have the same two products, carbon dioxide and hydrogen and water vapor, sorry. And then your reactant here is kind of the variable one. It's always got carbon and hydrogen and oftentimes has oxygen in there, but that's optional. So you can see some examples of some different carbon, hydrogen containing compounds that could be there. But that second reactant is always oxygen, and our two products are always carbon dioxide and water vapor. You can, yes, write it as water vapor and carbon dioxide, totally fine. But again, these are all combustion type reactions. By the way, this one right here is one of those cases where you have a combustion reaction really doesn't produce fire. This is what we would call cellular respiration, right? The breakdown of glucose with oxygen. So this is your food. This is what you breathe. And here's what you breathe out. So you don't literally produce fire inside your body, but you do release energy. So anyway, you still have that idea of heat and or light being produced from these combustion type reactions. So there you go. Those are kind of the 5 major structural types of chemical reactions. And there's plenty of others, plenty of other reactions that don't fit neatly into any one of these categories. We could kind of say it looks kind of like this, but kind of like that. Very, very common. So this is a very simplistic way of looking at introducing chemical reactions. Probably now that you're in an honors class, we need to start thinking about the more functional way of talking about chemical reactions, which is based on what we call driving force, and that's over here. So not just what does that thing look like on paper, but does it really happen? And if it does, why? There has to be a reason for a chemical reaction to occur. There has to be something that's beneficial, I guess, in a way, to the products in order to drive those reactants to change, to not to stay as reactants, but to turn into something different, to rearrange the bonds. That usually requires energy and of some sort, and then there could be some other things that can kind of help this happen. So typically, what's going to be causing it? Typically, there are some new forces. And again, this is the bonding that I'm referring to. Something new is happening where there's some different combination of elements that wants to be bonded together in a way that's beneficial for those. They're going to end up in a happier state, energetically speaking. And so that's one new thing, that those new atoms are either really strongly attracted to one another, or it's energetically favorable. And that's based on the laws of thermodynamics, energy is given off kind of thing. The second thing, and this kind of overlaps with it, the second major thing would be a transfer of electrons. That electrons going from one place to another, not necessarily just the bonds, but electrons moving place to place, can be an invisible driving force that would cause a reaction to occur. So here's an example of what this would kind of look like. So for example, with double displacement reactions, which are simply ion exchange, right? You're literally doing that foil, right? AB plus CD is producing this new combination, AD, if I can make that right, plus CB, it's a D. Well, why does this happen sometimes and not other times? Sometimes you put two solutions together and nothing happens. Sometimes you put two new solutions together and you see a change or some energy happens, it gets warmer or colder. There's two major driving forces here. And this would be the formation of these new products. Number one would be the formation of a precipitate. So now the precipitate would be a solid, and it usually just looks cloudy to us. It doesn't literally turn to a solid and like fall out, but it usually looks opaque, right? Or like a little swirl, like that very first picture that I showed, that orange kind of stuff almost looks like smoke. That's a precipitate. And a precipitate tells you that now these two new things have formed such a tight partnership with one another that their intramolecular attraction is so strong that they will no longer stay in solution and they fall out. They fall out as a solid. Similarly, one of your products can actually be water, and the formation of liquid water is a common driving force for acid-base reactions, where you have free-floating ions, but if you give hydrogen ions and hydroxide ions a chance to meet one another, their intramolecular attraction is so strong that once they form molecular water, they don't want to participate as ions anymore. They've sort of gone over to the molecular side, and they're no longer available as ions anymore. So formation of a solid or formation of liquid water. Formation of liquid water, by the way, is oftentimes invisible, but accompanied by a change in temperature, so you may not actually see it. The other one that you sometimes will get will be the formation of a gas. So if two ions come together, form a gas that bubbles up and out. That's another type of a driving force where a new product simply leaves. They're into each other so much more than they are to the rest of the reaction that they either settle to the bottom or they float to the top. Very common type. And then our last one here, this is about the transfer of electrons. And we're going to talk about this a whole bunch more in the second half of the chapter, but the driving force of transferring of electrons is actually probably one of the most important driving forces for chemistry in our daily lives. It truly is. I cannot understate how important this is. But the act of either gaining or losing electrons, shifting from being an element to being an ion, or vice versa, from being an ion to being an element, or from being one type of ion to another type of an ion. That's the change of oxidation state. That particular behind the scenes thing drives a lot of our electrical reactions that we see, and is actually behind many, many, many of our different types of chemical reactions. In fact, if we take a look back at many of our other earlier chemical reactions, most of those are actually redox reactions. Synthesis is redox, right? It's going from elements to ions. Decomposition is redox. It's going from ions to elements. Combustion is redox. We've got oxygen going from being an element to oxygen being present in carbon dioxide and water. And single displacement is redox. Again, you've got an example of a compound in an element, and that element switches and becomes an ion. The only kind of reaction that's not redox is double displacement, formation and precipitation. So there you have it. We are going to, in our next particular chapter, we're going to dive into these guys way more, and then we'll come back and visit acid-base reactions and redox reactions much more in the second half of our chapter. Thanks, and I will see you in the next video. Bye.